Good day, esteemed researchers and curious minds tuning in from around the globe. Today, we delve into the fascinating intersection of language models and robotics with our paper, VoxPoser, Composable 3D Value Maps for Robotic Manipulation with Language Models. We explore how to harness the power of large language models, like GPT-4, to guide robots in understanding and executing complex tasks, all without the need for extensive data collection or manual designs. Stay tuned as we unravel how VoxPoser revolutionizes robotic interactions. Let's embark on this journey of discovery together. Our research is driven by the challenge of grounding abstract language instructions in robot actions. Historically, methods have used lexical analysis, or language models, to parse these instructions. But these approaches have relied heavily on predefined motion primitives. This reliance has created a bottleneck, as these methods are often limited by the lack of large-scale robotic data. Our work aims to address this issue and push the boundaries of what's possible in the field of robotics. The challenge we face is that large language models, or LLMs, are unable to directly output control actions in text. These actions are typically driven by high-frequency control signals in a complex, high-dimensional space. To address this, we introduce VoxPoser. This innovative approach leverages the capabilities of LLMs to compose 3D value maps, guiding robotic interactions within the observation space. The beauty of VoxPoser is that it doesn't require extensive data collection or the manual design of each primitive. This makes it a practical and efficient solution for grounding abstract language instructions in robot actions. Diving into the technical details, our approach, VoxPoser, leverages the power of GPT-4 from OpenAI API. It operates by recursively calling large language models, or LLMs, using code they generate themselves. This process allows for a unique functionality for each language model program. To ground abstract language instructions in the visual space, VoxPoser uses perception APIs. These APIs provide spatial geometric information about relevant objects in the environment. The real magic happens when VoxPoser manipulates 3D voxels. It assigns rewards or costs at relevant locations, effectively guiding the robot's interactions with its environment. This innovative approach allows us to extract affordances and constraints from LLMs, providing a new way to guide robotic interactions. Our research addresses the challenge of grounding abstract language instructions in robot actions. We aim to harness the power of large language models, or LLMs, to enable robots to understand and act upon complex instructions. This approach eliminates the need for extensive data collection or manual designs for each primitive action. Let's take a look at the figure here. It provides an overview of our approach, which we call VoxPoser. In response to a language instruction and an RGBD observation of the environment, LLMs generate code. This code interacts with vision language models, or VLMs, to produce a sequence of 3D affordance maps and constraint maps. These maps, collectively referred to as value maps, are grounded in the observation space of the robot. These value maps then serve as objective functions for motion planners to synthesize trajectories for robot manipulation. The beauty of this process is that it does not require any additional training. In essence, we're leveraging the internalized knowledge of LLMs to enable robots to physically interact with their environment in a more intuitive and efficient manner. Existing methods for grounding language instructions in robot actions often face limitations. They heavily rely on individual skill acquisition and are hindered by the lack of large-scale robotic data. Furthermore, large language models, or LLMs, are unable to directly output control actions in text due to the complexity of high-frequency control signals in high-dimensional space. This is where our approach, VoxPoser, comes into play. VoxPoser extracts affordances and constraints from LLMs and composes 3D value maps in observation space, guiding robotic interactions. This innovative method bridges the gap between the theoretical knowledge of LLMs and their practical application in robotics. It allows us to leverage the wealth of internalized knowledge of LLMs, enabling robots to perform fine-grained actions without the need for extensive data collection or manual designs for each individual primitive. Our research introduces an innovative use of large language models, or LLMs. These models are capable of inferring language-conditioned affordances and constraints. They can also compose dense 3D voxel maps, grounding them in the visual space. These composed value maps then serve as objective functions for motion planners, enabling them to synthesize robot trajectories. Now, let's talk about the benefits of our approach, which we term VoxPoser. This method can learn a dynamics model from limited online interactions, making it highly efficient. It's also capable of handling contact-rich interactions, which are often challenging for traditional models. This makes VoxPoser a powerful tool for guiding robotic interactions in a variety of real-world scenarios. Our research introduces VoxPoser, a novel approach that harnesses the knowledge of large language models, or LLMs, to guide robotic interactions. This method addresses the challenge of grounding abstract language instructions into tangible robot actions, without the need for extensive data collection or manual designs. Now, let's delve into the role of LLMs in this process. They serve two crucial functions. Firstly, they infer language-conditioned affordances and constraints. This means they can interpret instructions and understand the implications for the robot's actions. For instance, if the instruction is open the top drawer and watch out for the vase, the LLM can deduce that the robot should grasp the drawer handle, pull it outwards, and avoid the vase. Secondly, LLMs compose dense 3D voxel maps for visual grounding. They generate Python code to invoke perception APIs, obtaining spatial geometric information of relevant objects. This information is then used to manipulate the 3D voxels, assigning high values to areas of interest and low values to areas to avoid. These value maps then guide the robot's actions, providing a practical and efficient solution to the problem of grounding language instructions in robot actions. Our research revolves around a process that involves recursive calls to large language models, or LLMs, using their own generated code. Each language model program, or LMP, is designed to perform a unique functionality. This process is further enhanced by the use of perception APIs, which are capable of obtaining spatial geometric information of objects. These APIs also manipulate 3D voxels to prescribe reward or cost, providing a dynamic approach to problem solving. We've implemented this system using GPT-4 from OpenAI API, a powerful tool that has greatly contributed to the success of our research. The composed value maps generated by this process serve as objective functions for motion planners, creating a streamlined and efficient system. One of the key highlights of our research is the demonstration of zero-shot generalization. This allows for the handling of open-set instructions and objects, showcasing the versatility of our approach. Furthermore, our method, which we've named VoxPoser, benefits from limited online interactions, enabling efficient learning and continuous improvement. This makes it a robust and adaptable solution for a variety of applications. Our research has yielded some significant results. We've developed VoxPoser, a system that successfully grounds abstract language instructions into tangible robot actions. This is a major step forward in the field of robotics. Moreover, VoxPoser has shown an impressive ability to generalize, even in zero-shot scenarios. It can handle open-set instructions and objects, making it highly adaptable to a variety of situations. We've also put VoxPoser to the test in real-world scenarios, where it has proven its worth in everyday manipulation tasks. This is a testament to its practical applicability. In addition to real-world testing, we've also explored its capabilities in a simulated environment. The results were equally promising, further demonstrating VoxPoser's robustness and versatility. Finally, VoxPoser has shown an impressive ability to learn more challenging tasks efficiently. This makes it a powerful tool for a wide range of applications in the field of robotics. In summary, VoxPoser is a groundbreaking development that has the potential to revolutionize how we use language models in robotics. In conclusion, our key contribution is the introduction of VoxPoser, a groundbreaking method that grounds abstract language instructions in robot actions. This innovative approach eliminates the need for extensive data collection or manual designs for each primitive, significantly streamlining the process. We've also harnessed the power of large language models, or LLMs. These models are adept at inferring language-conditioned affordances and constraints. They're capable of composing dense 3D voxel maps that ground them in the visual space, providing a robust framework for robotic interactions. In essence, VoxPoser and LLMs together offer a promising solution to the challenge of enabling robots to physically interact with their environment based on language instructions. This marks a significant step forward in the field of robotics and artificial intelligence. In our research, we've discovered that composed value maps serve a dual purpose. Firstly, they act as objective functions for motion planners, providing a clear goal for the system. Secondly, they enable the direct synthesis of robot trajectories that fulfill the given instruction, streamlining the process of task execution. We've also demonstrated the power of zero-shot generalization. Our approach is applicable for open-set instructions with open-set objects, making it versatile and adaptable. Furthermore, it proves useful for a variety of everyday manipulation tasks, showing its potential for real-world applications. This combination of functionality and flexibility makes our approach a promising avenue for future research in robotic interactions. In conclusion, let's revisit the key takeaways from our research. Large language models, or LLMs, have shown remarkable capabilities. They excel at inferring language-conditioned affordances and constraints, which are crucial for understanding and executing complex instructions. Furthermore, they can compose dense 3D voxel maps, effectively grounding them in the visual space. This ability to visualize and understand the environment is a significant step forward in the field of robotics. Now, let's talk about the functionality of these composed value maps. They serve as objective functions for motion planners, providing a clear goal for the robot's actions. This allows the robot to directly synthesize trajectories that achieve the given instruction. In essence, these maps guide the robot's actions, enabling it to interact with the real world in a meaningful and purposeful way. This research opens up new possibilities for robotic interactions, and we're excited to see where it leads. Thank you for your attention.